Hello, my name is Becca, and I'll be talking about the Archimedean property. When you hear the name, you may be thinking of this man here, but the Archimedean property was not, in fact, written or discovered by Archimedes himself. This theorem is credited to Eudoxus, a Greek mathematician on the right of the screen, who died almost 70 years before Archimedes was even born. The theorem didn't get its name until the late 1800s, when another mathematician named it after Archimedes in his work. Now, what is the theorem? Well, it is twofold, and here's what it says. Given any number x that exists in the real numbers, there exists n in the natural numbers satisfying n greater than x. And given any real number y greater than 0, there exists n in the natural numbers satisfying 1 over n is greater than y. So in order to prove this theorem, we must prove both parts 1 and 2. And so we can start with part 1. We will prove this statement by the method of contradiction. And so if we assume that this statement is false, then we know that the negation of this statement must be true. So the negation of this statement says that there exists some x in the set of real numbers such that n is less than or equal to x for all n in the set of natural numbers. Since there exists some number greater than or equal to x for all n in the set of natural numbers, this implies that n is bounded above. And so by the axiom of completeness, this implies that the least upper bound of the set of natural numbers exists. And so we'll call this supremum alpha. As a consequence, we can say that alpha minus 1 is not an upper bound of n. So this implies that there exists some n0 in the natural numbers such that n0 is greater than alpha minus 1, which then implies that alpha is less than n0 plus 1. But since n0 plus 1 exists in the set of natural numbers, we see our contradiction. We claimed at the beginning of this proof that the set of natural numbers was bounded above with a least upper bound of alpha, but we just found a number in the set that is larger than alpha. Therefore, the first part of the Archimedean property must be true since negation is false. So we have completed the first part. Now we can turn to the second statement of the property, which says that given any real number y greater than 0, there exists an n in the set of natural numbers satisfying 1 over n is less than y. And so since we have already proven the first statement, we can use it to help us here. So we will let x equal 1 over y. So then it follows that there exists some n in n, the natural numbers, such that n is greater than 1 over y. So taking the reciprocal of both of those sides, we get exactly what we were looking for. 1 over n is less than y. So we have now proven that both of these statements in the Archimedean property are true. And so this allows us to use this property in future real analysis proofs. This property is very useful in many aspects of real analysis and forms a very important part of many proofs for later topics and ideas. Some examples of its usefulness in real analysis arise when we try to prove the convergence of sequences, whether or not a sequence is bounded and or Cauchy, and when we try to find the limit points of sequences. So it is very important to be familiar and comfortable with this property so you can call upon it when necessary in future studies. Thank you for watching and have fun proving.